Okay. Yeah. Yeah, I'll get you that later. How about that? Okay. Okay, folks. Here we go, right? So yesterday we didn't quite get to finish example 7. Okay, didn't quite get to finish example 7. Talking about particle motion. Okay, this particular particle is moving along the x-axis. All right, we're given the acceleration for the function, and we're given information about the initial velocity. V of 0 is -3, and it started at the origin, so that means the initial position was 0. Okay, right? So we're asked, letter A here, to find the velocity function, v of t for any time t greater than or equal to 0. Given the acceleration function, to find the velocity, we would just want to integrate, right? And so we integrated using a U-Substitution here. All right, we got v of t equal to 2t minus 1 to the 4th plus c. Of course, that plus c, right, that means we're not quite there. That's the general solution. We want to find the specific velocity function for this situation. So we used our initial velocity at time 0. The velocity is -3. So 0 goes in for t. We set the velocity equal to -3, like this. C was -4, and so our velocity function was 2t minus 1 to the 4th minus 4. Okay? Then letter B, we were asked to find the position function, x of t. And again, the reason why they're using the x designation there, this is the typical reason why they use the x for position here, is because the particle is moving along the x-axis. Okay, so that's the traditional reason why you see that x of t. So otherwise, sometimes you'll see s of t for position, stuff like that. Anywho, do the same exact thing we did for letter A, except now we're integrating the velocity, get the position. We get a c, and again, use the initial position of 0 at time 0. So set the position equal to 0 at time 0 there, and we get c equals 1/10. Okay? You must show this like substitution here, folks. Okay, please show the substitution, all right? 0 in for your time, equal to 0 for the initial position, okay? And then, how you go about solving that, we get down to c equals 1/10, and so then there's our position function right there. Okay? All right, so letter C. Find the average velocity of the particle from 0 to 1. Okay, so again, we have two things that allow us to find the average of something, right? We have the average value, okay? If we wanted to use average value here, what function would we be integrating? If we want to find the average velocity and we want to use the average value idea, so let's say we want to do this using average value, okay? What thing are we going to integrate here? What function are we going to integrate? When we want to find the average value of something, we integrate that something. Okay? Average value, okay, is probably the most straightforward one, I'll say. If you want to find average velocity, you integrate velocity. If you want to find average position, you integrate position. If you want to find average acceleration, you integrate acceleration. You integrate the thing whose average you want to find, if you're trying to use average value here, okay? So it's going to be 1 over 1 minus 0, integral from 0 to 1 of the velocity function. Okay? Question?
So if you integrate position, what would that become then?
What, like, what's the conceptual meaning of that, I guess?
Yeah.
Starting point of 0.
I am not sure what that would be. Because I guess I don't have really a concept in my mind for like the position being a rate of change of something. It's not really a rate of change. So I think it wouldn't really have a meaning in our terms, okay? But understand though, right, so for example, if I wanted to find average position, I would be integrating position there, right? But I would be integrating the position, but then dividing by 1 minus 0, which is a time. So I'd still be getting position, but then divided by time, and so it would get back to just a position there, okay? So, I mean, it does kind of work out in a sense here. Just like here, I'm going to be integrating velocity. Integrating velocity is going to give me a position, but I'm going to divide it then by a time, so it's going to be position divided by time. It's back to a velocity now, okay? Because I have this 1 over 1 minus 0, which is a time value, right? 1 and 0 are both times. So, anyway, so there's the setup for average value. What about average rate of change? If I wanted to use that, what function would we be using for average rate of change? Position, because the velocity is the what? The rate of change of position. So if I think about the velocity here as being the rate of change of position, okay, rate of change of position, then I can use average rate of change here, okay, and I'll do it for the position. So it'll be x of 1 minus x of 0 over 1 minus 0. Okay? But if we look at these two things and compare them, we can see that they will be the same. If you integrate velocity, what do you get? Position. And then once we've integrated, what do? We plug 1 into the position, we subtract 0 plugged into position, and then we divide by 1 minus 0. These are the exact same ideas, right? We're doing the exact same thing here, okay? But from two different, kind of places. Average value of the velocity, we use velocity. Average rate of change of position, which is the velocity as well, we use x of 1 minus x of 0 over 1 minus 0. Okay? So there's the setup. Okay, I'm not going to, we know what the integral velocity is going to be. It's going to be the position. So we could just plug in, here and get that. So we could do it that way, or again, we could do it this way. I'm not actually going to do the calculation there. I think we're okay, right? I mean, we can integrate velocity. We have it already. It's the position, right? So I don't need to show that again. We just did it, okay? Same thing here. X of 1 minus x of 0, that you guys can plug 1 and 0 in there and divide by 1. I'm not going to worry about that one, okay? So is everyone okay with me not working those out? No one? Okay. Cares if I work them out or don't work them out? Okay. So letter D then, we'll look at this one. Find the total distance traveled. Okay. How do we find the total distance traveled of a particle or an object? Okay, so it's like net change. If we wanted to find net change, we would just integrate the normal velocity. Integral of the normal velocity. So again, remember, net change of position is the integral from 0 to 2 of v of t dt. Net change is the whole idea of if I moved left 1 and then right 1, my net change is 0. Because from my starting point to my stopping point, I have moved no units. Okay? Net change of position. My net change, my overall change is 0. Because where I started from where I stopped, it's the same place. Okay? That's net change. That would give us that. Okay? Total distance traveled, though, if I moved left 1 and then right 1, my total distance traveled would be 2. Okay? 2 because we're counting that left 1 as a positive, 1 unit, and then right 1 as a positive 1 unit. And so we want to integrate what here? The absolute value of the velocity to guarantee that all those negative regions, right, become positive regions and stuff like that. Okay, so that's the total distance traveled. Total distance traveled, okay, from 0 to 2. This one we're going to use our calculators for. Okay, I'm not going to have you worry about doing this without a calculator for this one. Okay. So again, yeah, good. I hear you guys keep calculators out. Good idea to type this in. Make sure you get the same thing. So 0 to 2, math, num, absolute value, and the velocity is 8. Oh, no. Velocity is 2x minus 1 to the 4th minus 4 dx. So I get about 24.725. Okay, 24.725. Nope. Crikey. Okay, so let's say hypothetically we wanted to try and do this like without a calculator or something like that. Okay, just real quick, I'll run through that and then we'll move into the next section here. Okay, well, I mean, what you would want to do is to figure out when your velocity, for what intervals your velocity is negative, all right? For what intervals your velocity is negative. So you would check to see, you know, when v of t, when this thing here is less than 0, okay? So you would solve this, all right, which isn't necessarily the easiest to solve, I guess, right here. In fact, that's probably why we wouldn't. Let's see here. I guess you could set it equal to 0 here. Let's see. 2t minus 1 minus 4 to the 4th, sorry, equals 0. So 2t minus 1 to the 4th equals 4. So 2t minus 1 equals the 4th root of 4. Okay, so you get this place here where your velocity is 0, this quantity, all right, and then you can check. Again, we're on an interval here from 0 to 2, right, only from 0 to 2. So you can check between 0 and 2, and then that 4th root of 4 plus 1 over 2, you could figure out, you know, where your velocity is positive, where your velocity is negative. And then you would integrate, you know, I think the velocity turns out to be negative here and positive here. So you'd integrate the opposite of the velocity here. So you would integrate negative integral from 0 to the 4th root of 4 plus 1 over 2 of the velocity here. And then you'd add to that the integral from the 4th root of 4 plus 1 over 2 to 2 of the regular velocity here. Okay, I know this is messy, but the idea here, right, is that we don't really know how to integrate absolute values. And the idea, well, we don't really need to integrate an absolute value of something. The way we would do this is instead just figure out where our velocity is negative. Okay, so the velocity is going to be, you know, negative on this interval here. This is the 0 of the velocity, the 0 of the velocity for this, you know, from 0 to 2. Okay, and so this is the interval for where the velocity is negative. So we know the velocity will be negative. So put a negative sign in front to cancel out the negative of the integral value there. So from 0 to 4, 4th root of 4 plus 1 over 2, and then the velocity starts to be positive on this interval, and so we just integrate the positive version of that. Okay, and work from there. That'll give you the same answer as you get right here for the absolute value. Okay, but of course, you know, it's going to be messy when you integrate that. You do have a position, so I mean, this could potentially be done without a calculator. It's just you wouldn't get a nice number. You wouldn't want to simplify the arithmetic for that one, right? You would want to leave it unsimplified. All right. Questions on any of that before we move on? All right, so again, total distance traveled, big idea, make sure you understand, right, is the absolute value of the velocity there. Very important, right? Net change in position is just the integral of the velocity. Okay. Let's move on here. Okay. So, next section here, we're going to be breaking this section up into 2 days as well. So the natural log function we're going to be looking at today and integration, okay, using natural log and integrating, okay, with U-substitution in it. Okay, so essentially, we're just extending our U-substitution here. Now we're going to integrate natural log, okay? So, what is the integral of 1 over x dx? The natural log of absolute value of x plus c. Yeah, don't forget the plus c. Okay, and don't forget the absolute values either, right? Okay? Then the integral of 1 over u du, which is equal to the same thing as the integral of du over u, right? Again, sometimes the book and problems will have the du up in the numerator when the numerator is just a 1 like that, but that's just because they're just multiplying the du up with the 1 there, that's all. So it's the same thing that those are saying. And what would this integral be? The natural log, absolute value of u plus c? That's it. Yeah, that's it. Okay, that is it. It's it. All we've done here is change variables. Okay, all we've done is change variables. So yes, it is the natural log of the absolute value of u. Okay, no question marks necessary. All right, so let's go on here. All right. Example 1a. Shh. Do we need a U-substitution for 1a? No. Okay, so how can we rewrite this though? What should we do with this 2 here? We can bring it in front of the integral sign, right? Make it 1 over x dx. And so this is just twice the natural log of the absolute value of x plus c. Okay.
What do?
Alternatively, yeah.
So when it says that, like, when will it tell us that we're solving for C? Or specifically say solve for C?
I see what you're saying. The directions will be something along the lines of find the specific solution to, the following integrals or something like that. Yes. You'll be given an additional piece of information, right? Because here, we're not giving anything in the directions except just to evaluate, and then here, again, we're just giving an integral. We'll have to be given some additional point, or something like that. Now, there's one other way we could write this. Let's harken back to our days of pre-calculus and think about the natural log and logarithm properties and stuff like that, and put aside the hate that you have for those things. But when we have a coefficient in front of a logarithm, what can we do with that coefficient? Yes, we can bring it inside as an exponent. That's not calculus, right? That's just a property of logarithms, okay? So we could rewrite this as the absolute value of x squared plus c. But then at this point, do we need the absolute value symbols there? No, because why? We're going to square the x. It's going to be guaranteed to be positive, and so we could ostensibly see this as a possible answer in our multiple choice. Even though we might be able to get to here and say, Mr. Wade, there's the answer, and you'd be right, the multiple choice might look like this. And so we need to be able to match from here to here, right? We're able to draw the absolute values here because x squared is guaranteed to be positive. There's no need to still have those absolute values there. Okay? All right. So this or this or this, they're all fine. All right, letter B. Do we need to use U-substitution here? I think we do. I think we do here. So let U equal 4x minus 1. du equals 4 dx. 1/4 du equals dx, right? We don't have 4 dx here, we just have a 1 dx. So I'm going to make this 1/4 du, so we can just substitute in for just the 1 dx that we've got right there. And so this becomes the integral then of 1 over u. Oops, I forgot the 1/4 out front there. 1/4 integral of 1 over u du. Bless you. Okay. And again, the integral of 1 over u. The natural log of the absolute value of u plus c. Yep, don't forget the plus c. Okay. And again, you guys did a really good job that one quiz where we did have those in our, oops. Well, I'm just going to fix it this way. Okay. Right. For the most part there. I put plus -1 because I wrote a plus and I didn't want to scratch it out and put -1. So I just made plus -1. Okay, so it works. Okay. We can do the same thing here. We can do the same thing here. We can bring that 1/4 inside. Okay. And again, in this situation, do we need our absolute values at this point? Will a 4th root of something yield a negative? No. So you're right, but we keep it real here. So. But of course, this is acceptable as well, and this one is too. All righty. All right. Letter C. What do you think here? U-substitution? Yeah, definitely. Okay, well, let's see here. So, yeah, use the quotient rule. You got it, Mario. You try that and see how it works out, okay? So, all right, anyway, let U equal, so what should U be? Okay, very good, right? It's maybe not so clear here, right? We don't really have something inside of something else unless you think about the fraction, okay? And then x plus 1 is inside the numerator of the fraction, x squared plus 2x is inside the denominator. We want to pick the denominator here, okay? Because remember that other kind of guideline we have for our u is we want to find our derivative as well. And the derivative of x squared plus 2x might be something around x plus 1. So let's see if this works here. Okay, and so the du will be 2x plus 2 dx. Okay, like that. Do we have 2x plus 2 dx? No. No. So what can we do here to get what we have, the x plus 1 dx. Factor out that 2. So du equals 2x plus 1 dx. And we can divide the 2 over. 1/2 du equals x plus 1 dx. Okay. And so then we've got our x plus 1 equals that. So we have 1/2 integral. Okay. And what will the integral? It will be the integral of what? 1 over u. Yeah, exactly right. It's going to work out to be 1 over u du, which then is 1/2 the natural log of the absolute value, x squared plus 2x. Okay. Wow, I kind of jumped a step there. Maybe I shouldn't have done that. Let me not do that. Natural log of the absolute value u plus c, and then 1/2 the natural log of the absolute value of x squared plus 2x. Okay, there we go. Okay, again, if we wanted to, we could stop here, but we can also see, because of the properties of natural logarithms, we can make this x squared plus 2x to the 1/2 power, which is the same thing as just the natural log of the square root of x squared plus 2x plus c. And again, we can drop those the absolute values here because the square root, right, we're not going to have a negative value here. We just get the principal root there. Okay. All right. Letter D. 1 over t times the natural log of t. Okay. So, probably U-substitution. What should u equal? Okay. If u equals t.
That sounds wrong now.
Right. Because of the way I said it, probably, right?
Yeah.
I like David Way. I got to work on my poker voice, I guess. Okay. If we let u equal t, all we're going to end up with here is essentially a change of variables. Okay. I'll give you a little hint here, right? Like u will never equal a single variable because all you're going to do is just rewrite this thing that's in terms of t and directly in terms of u, right? Because du here will equal dt, and all you're going to do is just make it this. Right? If you let u equal t, all you're doing is changing the letters around. So it's not going to be useful here, okay? So just a little hint, you'll never let u just equal a single variable like that. Okay? But Sarah, did I hear you make a suggestion?
Let it equal the natural log of t.
Yes. So let's let it equal the natural log of t. Okay? Sarah, did you have any, what was your strategy there? How did you know that natural log of t might be a good candidate here?
Well, I knew if you take the derivative of natural log of t, that'll equal 1 over t.
And there's that, yeah,
and
that
would
1
just
over
leave
t
you with
dt
1
right
over
there.
u, so that's
Yep. Very good. Exactly right. Okay. Again, you want to look. That's why it's so important to be good with those derivatives, right? You want to find the derivative of your u also in your integrand there. So du equals 1 over t dt. We have precisely 1 over t dt here, and so this will equal the integral of 1 over u du. Okay. Which is the natural log of the absolute value of u plus c, which is the natural log of the absolute value of the natural log of t plus c. Yes, natural logception, exactly right. Okay, natural logception. All right, and this is where I can whip out an awful calculus joke too, so we'll do that here real quick.
Cringeworthy.
It's really not great, but okay. So what would the integral of 1 over cabin d cabin be? It would be the natural log of cabin plus c. It's a houseboat. It's the natural log cabin plus the c, the water, and the boat. I knew you would appreciate that one. I knew you'd appreciate that one. Yeah, exactly. Let me show you this terrible joke. All right, so moving on. had the exact same reaction when I was showed that in my calculus class. I was like, okay. So anyway, now this tradition has been passed on. Okay. So, we got definite integrals now. Definite integrals, okay? Do we need U-substitution for letter A? Okay, yes, I hear. So what should we let U equal then?
Oh my god.
Yeah, let U equal x. No, let U equal, what's that? E to the x, okay. So we do e to the x here. The derivative of e to the x is e to the x dx. This e to the x is already our u. We need another e to the x dx here. The only other e to the x is this e to the x, but it's in the denominator. It's like 1 over 1 plus e to the x. So we don't quite have this derivative of our u that we picked. So maybe we don't want to use this one here. So what else might we want to use here for our u? Yeah, the denominator. Let u equal 1 plus e to the x. Okay? Then du will be e to the x dx. Does that make sense there, Clayton? You see that now? Yeah. Okay, so it'll be the integral here. We have exactly that e to the x dx there. So this is literally just going to be 1 over u, excuse me, du. Okay. I'm going to change our limits of integration here. Okay, again, if you don't like doing that, if you want to integrate this indefinite integral, then rewrite it in terms of x, then you use your x limits of integration, feel free. But I'm going to go ahead and change them up. Okay, so I'll plug the lower limit in here. E to the 0 is 1 plus 1 is 2. Okay, good. And then plug in 1. E to the 1 is just e. So 1 plus e is our okay, limits of integration there. And so then the integral of 1 over u, natural log of the absolute value of u. We don't need to put a plus c in because we're doing a definite integral here. Okay, so we integrate, yep.
Can you explain, like, mathematically why the du disappears?
Why the du disappears? It's kind of, I guess, for the same reason why, like, the dx disappears here, too. Because, let's see here. How do I want to describe this? I don't have a good answer for that right now. I'll get back to you on that, though. Yeah. I don't have a good answer for that. Yeah, I don't have a good answer for that. I'll get back to you on that, though. Okay. So, natural log of the absolute value of 1 plus e minus the natural log of the absolute value of 2. Okay. Natural log of the absolute value of 1 plus e, is it necessary to have the absolute value symbols here? No, because 1 plus e is always going to be positive, so we could just rewrite it as that. Okay. Likewise, is it necessary for the 2? No, we can do the natural log, or the absolute value of 2, it's just 2. Right. Again, now, cast your memories back to pre-calculus. When we subtract 2 logarithms, what can we do to simplify that? Division in a single logarithm. Exactly right. Like that. Right? So, yes, Urja. No. But, multiple choice. If multiple choice answer is written like this, you need to be able to get from, what you have to what's there. So that's why I'm presenting that. But of course not Urja. Yeah, you can stop right here, or here, or here. Right? Any of those are good. Yes, you could calculate it out if you wanted to. Okay, question, Gabe?
We never have to switch back into adding in 1 plus e to the x, because when we integrate with u, if we don't have to go right back, so anyhow it's back to x.
Correct. If you, so let's say hypothetically, right? Hypothetically, you didn't change your limits of integration. You left these blank. You just integrated 1 over u to get the natural log of the absolute value of u. Then you resubstitute in the 1 plus e to the x. So in other words, you have something like this. Right? And that we're going to evaluate from 0 to 1. When you plug in those limits of integration, you're going to end up with 1 plus e and 2. So it end up being the same thing. Okay, this just kind of like jumps that step. Okay, so all right, letter B. Letter B. Okay, do we need to use a U substitution here for letter B?
No. Just by that.
Do we?
Yes.
Yeah, we can just divide each one, right? Okay, we have a numerator. We can break it up over that denominator 2x. Okay, so it's like a little twist in here. I'll make it real, blatant there, right? Okay, we can break up that numerator over the denominator. And so this is just the integral of 1 to e of 2x plus 1/2 x to the negative 1 dx, right? You do want to rewrite that 1 over 2x there. Actually, I guess you can leave it as 1 over 2x. That might actually be a better way now that I'm thinking about rethinking what I'm doing here. Maybe we'll do 1/2 times 1 over x. I like that better. 1/2 times 1 over x maybe instead. Yeah, it's a better way to write it. Okay. What is the integral of 2x? Well, it's going to be 2x to the second over 2 plus, and then 1/2. What's the integral of 1 over x? Natural log of the absolute value of x. Okay, and again, no plus c necessary because we are integrating a definite integral here. So integrate from 1 to e. So e squared plus 1/2 natural log of the absolute value of e minus 1 squared plus 1/2 natural log of the absolute value of 1. Okay. What's the natural log of e? 1 times 1/2 will give us 1/2. So we have e squared plus 1/2 minus 1 squared is 1. What's the natural log of 1?
0.
Times 1/2 will still be 0. Okay, and so we get e squared minus 1/2. Right? 1/2 take away a 1, we negative 1/2. Final answer there. But again, if it's free response, you're done right here. But it's multiple choice. You'll be able to match what the multiple choice has for you there. Okay. All right, let's take a look at letter C here. Why don't you guys go ahead and try letter C? Give that one a try. I've been doing plenty here.
Gotta give us the trick.
I'll give you a help, right, or a little tip, right, or give you a start, okay? What, is this a U substitution? Do we need it here?
Of course.
No.
Better safe than sorry.
Yeah.
Okay.
No.
Yes.
It's one of the.
Yes, you do?
Yes.
Okay, so if you're saying so definitively yes, what is your U going to be? Tangent. Tangent theta. Yep. Let U equal tangent of theta. There's your hint, okay?
Isn't that good there? He tried to correct me on my triangle, and so I hit him with my pencil. I took my own action.
Yes. Try to use your words next time, all right?
Yeah. I tried to, but he wouldn't listen to me, so I fell. You need to
Gotcha.
wake his brain out.
Force was necessary.
Yes. Yes.
It put my brain down, not woke it up.
Put you in a nice little corner.
Okay. So, if we let u be tangent of theta, du be secant squared of theta, d theta, okay? That 9/7, I pulled that coefficient of 9 over 7 out front, make it just 9/7, or 9 in the numerator, 1/7, right? So 9/7, okay? That leaves us with 1 over u du. I went ahead and changed my limits of integration as well, okay? Tangent of pi over 4 is 1. Tangent of pi over 3, right, is root 3. Okay, integrating that 1 over u, natural log of the absolute value of u with a 9/7, integrating, or evaluating from 1 to root 3. Plug in the root 3, plug in the 1. Natural log of 1 is 0, so that lower limit's gone. Okay, and then natural log of root 3, you could leave it as just 9/7 natural log of root 3. Right, you can drop the absolute values because root 3 is going to be positive. Or square root, right, is the exponent of 1/2. If 3 is to the 1/2 power, you can bring that 1/2 out front alternatively, right, and make it 9/7 times 1/2, which is 9/14 natural log of 3. So again, either one of these, right, or of course this previous one right here, are acceptable, but just again understand with those natural log properties, right, or the log properties, not just natural log, but log properties in general. Okay? Questions on any of that? All right, let's do this one right here. I'm gonna make myself some space. All right, letter D. Do we need to use a U-substitution here?
What's the dual? I say yes.
Do we need to use U-substitution here? Yes, okay. We're going to let U equal what then? Yeah, 5. Yeah, I let U equal dn. All right, that's the 5 minus n squared, right? It's inside the square root there, so it's 5 minus n squared. So du will be negative 2n dn. We have a 3n dn. Let me go ahead and just change this to be 3 in front, and then be n over square root of 5 minus n squared dn. So I'll pull that 3 out there. So we have an n dn. I need this to be n dn, so I'm going to divide the negative 2 over, make it negative 1/2 du equals n dn. And so this becomes then, let's see, I'll go down here. Negative 3/2 in front. Integral, we'll worry about the limits of integration in just a second here. There's our du, so 1 over the square root of u, right, du. All right, limits of integration here, we'll plug these in. So 1 in for the n, and so 1 squared is 1, 5 minus 1 is 4. 2 in, 2 squared is 4, 5 minus 4 is 1. So the integral of 1 over square root of u, of course, is the natural log of the absolute value of u. No, Mr. Wid. Integral of 1 over u. 1 over u to the 1 is natural log. Integral of 1 over the square root of u, that's the same thing as u to the negative 1/2 du. We add 1 to our exponent here, it becomes u to the 1/2 over 1/2. Evaluate it from 4 to 1. Okay. Watch out, right? Watch out. Just because we have a fraction, don't automatically assume it's going to be natural log and stuff. In this case, right, we have a square root in our denominator, which makes it u to the negative 1/2 then. Okay, and so this becomes then negative 3 times 1 to the 1/2 minus negative 3 times 4 to the 1/2. Okay, so negative 3, let's see here, 4 to 1, 2, 6, so plus 6, so 3 is our final answer there. Okay, 3. That's it. All right, we're going to do the next problem, and then we'll be done. Okay, just one more thing. Talking about the Yule log and the roll, whatever. You'll see on the next page there. Okay.
Oh, shit.
Some calculus punnery, I guess, or whatever. So letter D. Here we go. Santa's favorite elves are tasked to create the best gifts, the calculus ones.
This was timed perfectly.
It is, because it's the same.
Yeah, or like roughly this is about that time when it happens. This kind of thing happens. So yes, it works out that way. All right. The second most popular gift is the Yuletide log behind the pumpkin roll. See, it's spelled like Rolle's theorem. Ha ha. So anyway, the elves realize they must increase their production rate to this, where y of t is measured in millions of units per day. So this is the Yuletide production rate. Okay, this is the production rate. And t is days since December 20th. All right, because of course they're under the gun. All right. So given the elves have and so December 20th is t equals 0 there. Given the elves have already made 73 million by 1220, how many would they have produced by the time Santa leaves on Christmas Eve, 1224? So why don't you guys go ahead, set up your integral here. Set up your integral. Just set it up. Just set it up. Just get the setup, okay? So they already have 73 million by 1220. And then how many on 1220, which is when t equals 0, how many will they have then by Christmas Eve, 1224? So just go ahead and set this one up, and then I would like you to, I would like you to evaluate this one by hand, okay? Don't use your calculators for this. Try and do it by hand. Or at least get you don't have to simplify the final answer if you don't want to. You can just leave it, the arithmetic unsimplified, but do this one by hand, okay? You can do it by hand. So please do. So again, if you feel like you got it set up correctly, go ahead and feel free to solve the integral by hand. Try it without a calculator. You can use your calculator to check it if you want, but try and solve this by hand.
picture of one
The
of the
metaphor.
problems on the
The
other side?
metaphor. You're not a bad kid. What's that?
Can I get a picture of one of the problems on the other side? Thank you.
Sure. No problemo.
I'm gonna drop this class.
Okay, make sure you give, please, units.
I can't do 5 squared plus 1. I said it was 25.
Not looking. So you don't need to convert into 73 million.
No, you got
Just
the
at
20th,
73.
the 21st, 22nd, the 23rd, and the 24th. That's 5
So,
days.
no, because if you notice here, this thing, the rate is given in millions per day. So this number, like you
But
get like
then
a
you also
3
got
for
from
this,
day
it'll
one.
be 3 million per day. So you don't need to convert 73 to 2 million, you need to
It's 5.
Okay, right, well, I'm gonna start this there, okay, so that makes sense.
I swear, lenders
Okay,
only
no,
borrow
integral at 0 to 4, perfect, so y of t, exactly right.
You start at t
He
equals 0.
is
You
since
do want
December
2 squared plus 1.
Exactly.
And then that's right, so now you need to rewrite your limit.
December 21st will be 1.
So equals,
That's what we're saying.
that's what everybody now let's write the x equals to 1 half and the 417 in the right? Because the 417 is coefficient, you pull that out, 1 half are only substitution, right? Right, you follow me with that? So let's write
That's day 1. That's day 2.
That's
That's day 2. That's the 24th. That's 4 days.
We're integrating numbers, now we gotta be careful because
Did
you
you
really
really, did you just leave it like how you wrote it? Or did you actually like solve it all the way?
right. So plug in your 0.
Yeah. Wait, you approximated?
Right, and then plug in 4.
You use a shot.
There you go. Okay. So your d2 is t dt. That's going to take care of your dt here. And then there's your u right there. 1 over u. Du. You see that?
Tell her what that
So
diameter
let's
is looking
make
at.
sure you can count it. Right, the 417, we pull that out front. So it's just t over t squared plus 1 dt, right? The t dt, t dt here, there it is. There's your du, so there's your du. And then what's a t? 1 over t squared plus 1. T squared plus 1 is u, so it's just 1 over u.
I'm going with day 5 days.
It's not 5 days.
It's definitely 5 days. When you count math problems, you count the first one,
That was a separate problem. That's
You're not gonna get it through later set. He never does. He will never set it.
this one now, we just
Learn that from the
what
guy
is the
that
integral
sits
of 1
right next to
over u?
him. When I had to literally draw a triangle to show him that he was wrong.
But you were still wrong.
But I had
What's
to
the
draw a
integral of 1
triangle.
over u? You just plug the t, yeah, natural log of the absolute value of u, and you're going to evaluate it from 1 to 17.
I just put my numbers.
Okay, so erase the 0 and 4, right, because those are for right. So, this relates your t's and your u's. So 0 is the t limit of integration, you can go in for the t here. 0 squared is 0 plus 1 is 1. So your lower limit is 1 in terms of u. Yeah, exactly right. Alright, like one more minute here, one more minute. We'll go over this.
0.72549.
Yes, go ahead.
4982. You have to be exact because Santa Claus is expensive.
Well, too bad you ain't getting that 0.7 toil.
That's a challenge has to go.
Well, but remember though, 0.7 in this case is like, well, 0.7 million toys. So that actually counts, you know,
Yeah.
700,000
So
toys.
in Africa's
Natural log of 1 is 0, right?
Correct. Yes.
Either which way I said it wasn't gonna be nice.
Okay.
Well, don't just take the toys from Americans because we're all spoiled brats and we don't need it.
There will be the work. Okay, there be the work.
I just Andrew, you're wrong.
Mr. Wade, we need you to explain something to Lander. That on day 1220 is not count as a day.
Okay, yeah, 1 second here. 23,
It's
55.
days since December 20th.
Exactly, you can think of it that way.
You don't count December 20th.
Always.
I agree, though, Landry. It can be a little, like, I don't know, confusing sometimes, and maybe we aren't always most accurate with it.
You know, at the school they offer some assistance.
But yes, time t equals 0 to the 24th. Okay, if it's 20 to 24, that's 4 days. Yes.
But it says that they may have already buy it. Not saying that that's included.
Aha! Thank you, Sean.
You're really? She was like, well, master good. She was like,
I see what you're saying here. So, December 20th is day 0, and then to the 21st, that would be 1 full day, right? 20 to 21, and then 21 to 22, 22 to 23, 23 to 24, and so then on the 20, so that's still 4 days.
When you leave it,
I don't know, maybe he left.
Potentially, but maybe he left. Yeah, I mean, we don't know exactly, but I think 4 is the way to go here. I understand what you're saying though, but I think 4 is the way to go. I think it is. So yeah.
So the 73 like always needs to stay out front, but then the 417 times like the 1/2 needs to go in front of like both of them. 'Cause I
Right.
just had like everything out front.
So the integral, right? We're adding the integral. That 417 is a coefficient for just the integral, not the 73 as well. 73 is not part of the integral; it's separate. Yeah. Same thing with 1/2.
And then so then you need to multiply 417 and the 1/2
Times the answer, times the what we integrated here, yes. But only this, not the 73. 73 stays out front, plus, and then I put parentheses kind of grouped together what we this evaluation here. Okay, yes?
So why does the 73 just like stay by itself?
You would combine like all of them, 73 and
So you eventually you do combine everything right here. Okay, but so this makes sense to you why this is this way?
No, like that was my question, because like I did it where I did like, so the one right above that.
Right here?
So I just plugged in 17 and one for that whole thing, like including the 17.
So you did 73 plus this natural log of 17 minus 73 plus this natural log of 1. I gotcha. Be careful here though. What we're evaluating from, and maybe I should do a better job here of indicating what we're evaluating. That quantity is be evaluating from 1 to 17. And maybe that's a better way to write it. Okay?
I did like 73 plus 417 over 2 times the natural log of 17 minus the natural log of 1.
So that would work if you...
And like I had the parentheses. Yeah, no, okay, so that would work too.
Yes, because the 417 over 2 would distribute to both terms. It gets you the same thing as that. Okay, folks. That's all. Okay? Homework is posted on Google Classroom. Of course, there's problem set 5 for us to be working on as well. Okay.